get started. I'd like to welcome Geraci here to give his first talk. It's going to be about, I think, some background on doing precision force sensing with these oscillators. So, let's take it away.
It's a pleasure to be here. I'd like to thank Casimir for the invitation, and it's been great to hear all the other outstanding lectures. So, I'm going to talk about basically applications of mechanical and optomechanical systems, in particular using them to measure small forces. And so the outline for the three lectures, basically, the first lecture will discuss precision force sensors in general using mechanical oscillators, give some background information, also some examples of measurements that have been done for particular types of different types of physics. And then we'll move to laser cooling and trapping of dielectric objects. In particular, we'll look at the context of force measurement using these levitated optomechanical systems. And I'll talk about some of the work in our lab where we're building up an experiment to test some of these ideas. And in the final lecture, I'll discuss some particular experiments that we're hoping to do. First of all, measuring the Casimir effect in some new regime, and then also a test of non-Newtonian gravity. And at the very end, I'll talk a little about a very recent idea which involves using these levitated optomechanical systems as a new way of measuring gravitational waves at high frequencies. Okay, so for the first part, we'll discuss force measurement in general using these oscillators. And so we'll talk about some of the fundamental limits. In particular, thermal noise tends to be a significant limiting factor in measurements in practice. And then we'll talk about some examples of different physics that want to do with these oscillators. So short-range tests of gravity, detecting spins in magnetic resonance force microscopy. And then I'll say a little bit about another experiment we're doing in our lab where we're investigating detecting spins of whole atoms using mechanical oscillators. And then from there, I'll discuss pushing the sensitivity limit, and this will lead us into the discussion of these levitated systems. Okay, so to set the scale for those of us that aren't in the precision measurement community, just to put some idea of what kind of numbers we're talking about here. So imagine you have a person that will weigh, say 70 kilograms, and they stand on a scale. So the Earth's gravitational field, they exert a force of about 700 newtons on that scale. If you have a scale that's very precise and has a well-calibrated spring or something, maybe you could measure a resolution of, say, 10 to the minus 1 newtons with that scale. But now suppose I wanted to be able to tell the difference in the person's weight if a single dust mite comes along and lands on the person's head. So now I would need to be able to make a force measurement with a resolution of about 10 to the minus 7 newtons. And so, of course, for smaller objects, I need even more sensitivity. A single bacteria would be something like 10 to the minus 15. A single virus, 10 to the minus 19. A single carbon atom would need to be able to measure the force at the level of 10 to the minus 25 newtons. And so the state-of-the-art level for force measurement in these kinds of mechanical sensors is at the Atto-newton scale, which is around 10 to the minus 18 newtons. So this just gives you a little bit of the scale of how small forces we're talking about measuring. Of course, in practice, this is what one tends to do with these oscillators. So in practice, they're used for such things as single electron spin detection. So this is a figure from some work done at IBM, Almaden, and Dan Rugar's group, where they do magnetic resonance force microscopy. They basically take a Cantilever beam and put a magnetic tip on it, and are able to detect the force from a single spin in a single electron spin in a solid that's at less than a micron distance away from that tip. So one can also use this, and I'll say a little bit more about how this works later in the talk. One can also use these devices to measure gravity at short distances, for example, putting one of these Cantilever beams with some sort of a test mass, and then looking at the gravitational interaction between that mass and some other nearby mass. And so since I'm going to say more about this later as well, let me just explain why this is a challenging problem that requires such high sensitivity. So if I just have two spherical masses here, M1 and M2, they're separated by some distance, then I have some Newtonian gravitational potential that goes like the product of masses divided by their separation. But if I try to scale things down and make things really small, the forces involved from this potential get quite small. So the mass here is limited by the finite density of material on Earth, and the mass is basically given by the density times the volume of the object. So if I have two spheres that are separated by twice the radius, so they're as close together as possible, and radius r, I can look at how the Newtonian force between these two balls scales with this size scaling problem, and you'll see that it actually goes like Newton constant times density squared times the distance of a positive fourth power. So you might be misled looking at this formula thinking, well, things get strong, all you do is bring things close together. In fact, because of finite density, things get actually weak very rapidly once I get two masses close together. And so if I have masses that are separated by, or the size scale is 100 microns, this force is already down to 10 to the minus 17 and scales are dwarfed. So if I wanted to test gravitational force even at smaller distances than the force I need to be able to measure is significantly less than that. And so why do I want to do this? Well, there's some theories from high energy physics which suggest that the Newtonian potential isn't the full story. In fact, at short distance, certain theories predict that there's going to be a correction to this Newtonian potential in this form, where one has 1 plus some dimensionless factor alpha, which describes the strength of some new interaction relative to the Newtonian gravitational potential. And then also times this exponential, e to the minus r over lambda, where lambda is the length scale that this new interaction occurs at. So in other words, this is the constant wavelength of the new particle that's being exchanged. There's some new particle physics that's giving a correction to this Newtonian force between two nuclei. And so some theories in particular, some of them involving supersymmetry, some of them involving string theory, some of them involving large extra dimensions in space, suggest that below the length scale of around a millimeter, one can expect to see this sort of deviation from this Newtonian potential with this factor here alpha varying from anywhere from 4 to 1, being a force basically of gravitational strength, up to say 10 to the 6 or even higher. So the forces, for example, that would be 1,000,000 times stronger than gravity, but would only really turn on if you got your masses closer together than this interaction length scale. Okay, so more on this later, but let's look at the cantilever now as a force sensor. So the cantilever, we can basically think of it as a spring, right? It's we've seen a lot of this now, so a whole lot of time when you apply a force at the tip of this diving board, we get some deflection. There's some sort of a force constant K, which describes how much the tip deflects under the influence of that force. So in practice, it's slightly more complicated. You can pull out Lifshitz theory of elasticity and figure out that the modes of vibration in this rectangular oscillator, there's a fourth order differential equation that describes the displacement x along the length z of the oscillator as a function of time. And so the modulus times this moment of inertia times the fourth derivative of this x displacement is given by the minus density times the cross-sectional area times the second time derivative. So you work all that out and look it up and you'll see that the normal modes of this cantilever vibration go like 1 over the length squared and then times the square root of the Young's modulus times the moment of inertia divided by density times the area. And the modes are spaced non-uniformly as they would be for a simple harmonic oscillator. And the shape of each of the modes is given here. So the fundamental mode looks like we used to have the end of the board vibrating. The second mode has a node in it. Next one has 2 nodes, et cetera, et cetera. In practice, what we're going to be talking about is only this fundamental mode here. We can describe some effective mass to essentially treat this vibration as a simple oscillator. So if I look at the force constant of the cantilever, it goes like the Young's modulus times the width of the cantilever beam times the ratio of the height over the length cubed. And so I can define some resonant frequency now where it's the square root of k over this effective mass. And it turns out this effective mass is about a quarter. So it basically acts as if a quarter of the mass is concentrated at the tip, essentially. And of course, if I add additional masses to the end of this thing, then that changes the frequency accordingly. Okay, so dissipation, we've heard a lot about in these lectures. So it also plays a very crucial role for force detection. And typically, parameterize dissipation by this quality factor of the oscillator, which is given by the ratio of the energy in the oscillation over the energy dissipated in the cycle times 2 pi. So in terms, I can also write it in terms of mass and spring constant and the damping parameter of the oscillator, gamma. And so this is going to play a central role, as we'll see in a moment. So if I have my force detector and I apply a constant or a DC force, basically I just get a deflection that looks like k times x. Or sorry, I get the deflection that looks like the force over k. But if I have a force that's varying, a time dependent force that's varying at the resonance frequency of the oscillator, now I get an enhancement of motion that's given by the quality factor. And these kinds of devices, these Q factors can be quite large, so like 10 to the 5 or 10 to the 6, depending on what kind of system. So this is really a nice handle where you can generate a large displacement for a small input force. So if I have a harmonic driving force, let's just say it's a simple harmonic force at a particular frequency, I can solve this differential equation for the motion of the cantilever, and I can define the mechanical susceptibility, which has already been, I guess, Ash Clark defined this earlier in the series, where this is the ratio of the displacement divided by the force, and it has this sort of form where if I look at DC, where the frequency goes to 0, then what you expect is in fact true. The displacement of the cantilever looks like the DC applied force divided by the spring constant. And in the high frequency limit, this susceptibility goes like 1 over mass times the driving frequency squared. So activity tends to decrease at the high frequency. In fact, this is the principle behind a lot of passive vibration isolation systems. Okay, so I can look at, here's the susceptibility again, and I can look at the steady state. So I'm going to ignore transient effects. I'm going to assume I have some oscillating driving force that's on for some time, and I'm going to look at the particular solution of this equation. So if I have this, in the presence of this driving force, cosine omega t, I can write the amplitude as the force times the absolute value of this susceptibility times cosine omega t times some phase function. So here I'm just writing the susceptibility as its amplitude times e to the phi by some phase factor. And so this amplitude here, the absolute value of the susceptibility is 1 over the mass times this function here. And the tangent of this angle goes like omega times the damping coefficient divided by omega squared, omega squared. And so I can write this another way, so I can look at the amplitude of the response of force at a particular frequency in relation to what the amplitude would be for a DC force. And so I could write that as the ratio of this amplitude divided by the DC force goes like the frequency squared divided by the square root of this factor here. In the denominator here, I put Q back in just using that omega naught over Q. So I thought F here should just F related. So that this is 2 pi. That equation is still fine. And also, so there's dissipation. So if I look at the power dissipated in my harmonic oscillator is given by the force times the velocity. So I can look at my steady state dissipated power, and it's going to go like omega times the force squared times this magnitude of susceptibility times sine of this phase angle. I can also write that as 1/2 times the force squared times omega times the imaginary part of the susceptibility. Where the imaginary part of the susceptibility looks like omega times the damping constant divided by this denominator. And on resonance, it looks like the force squared divided by m gamma. Okay, so the fundamental limit in terms of how small a force you can measure with these oscillators comes from thermal. So if you have your, imagine I have some cantilever beams in contact with a thermal bath. You understand this with a nice analogy to Brownian motion. If I have a dust particle that's wandering around through a fluid, I have fluid molecules which will randomly collide with dust particles to give it a bunch of kicks. Right? So here, the cantilever is in contact with the thermal bath. Just due to the higher temperature, random kicks are given from the cantilever beam. If I write down the equipartition theorem, I can derive this in a moment, that the minimum detectable force I can see in the presence of this thermal kick goes like kT, the temperature, times the bandwidth of measurement, times the spring constant, divided by the Q factor, times the frequency oscillator, also 1/2 power. Okay, so this is a fundamental result that's very important, so let's go through the derivation. So with the thermal force, I have a white noise background, right? So I have noise at all frequencies. So there's some force spectral density. And through this mechanical susceptibility, I can get some position spectral density as a result of responding to this white noise force. So I can calculate this x squared, the average value of the RMS position fluctuations of my oscillator, as an integral times this force spectral density times this response function, where I have susceptibility, where I have this amplitude as a function of frequency divided by the density amplitude, and I can integrate this up to overall frequencies and then divide by the spring constant to get my average RMS displacement. So if I do this integral, I find that this goes like 2/pi q times resonant frequency square root times k times x RMS. And now using the partition theorem, I can relate this to the temperature, and therefore I find that this force spectral density goes like 4 times the spring constant times T over omega q. And the minimum detectable force you can see is simply the product of that with the bandwidth, and leads to the expression that we showed on the previous slide. So this is a manifestation of the fluctuation-dissipation theorem. So in equilibrium, thermal fluctuations are related to dissipation. And so I can rewrite this formula as this force spectral density is 4kT times some damping parameter, mass times the gamma, where gamma here is the frequency divided by Q. This is very much like Johnson noise in a resistor, where you have voltage fluctuations given by temperature and resistance. So in general, the fluctuation-dissipation theorem tells you that the spectral density of position fluctuations is given by kT times the imaginary part of susceptibility divided by omega. And I can use this form for the imaginary part of susceptibility and this expression to arrive again at this result. So there's also a quantum version of this. So this, what I told you before, was true for a classical oscillator. So in the quantum limit, one needs to replace kT with this h bar times this cotangent function. So in practice, the applications I'm going to be discussing, the force measurements I'm going to be talking about, are all in the regime where we're still in the classical limit. There's still some finer temperature of the bath, and I haven't cooled my oscillator down to a single phonon level, so it's really the previous equation that's relevant. So I'm not going to spend too much time talking about this also, because looking back at Clark's lectures, he described a lot of these quantum effects already in some detail. But let's look at what happens to my classical formulator for force sensitivity in the limit that I have some kind of a laser cooling mechanism, so some kind of a feedback cooling or some kind of cap pull. So in this case, this formula is now replaced with the temperature replaced by some effective temperature of particular load vibration we're looking at, and the Q factor is now replaced by some effective Q factor. And so the new Q factor here is provided by damping from my cooling mechanism, whether it's active optical feedback cooling or cavity cooling, for example. And so these mechanisms work by damping the motion of the oscillator while at the same time reducing the temperature of the motor. And so the effective Q is given by the initial Q essentially times the ratio of the mechanical optical cooling line widths. And for the large part, there's some corrections here I'm neglecting, which we'll talk about later. The temperature is reduced. The final phonon occupation number is reduced by the same factor. So largely speaking, one gets to, when one applies one of these feedback contexts, one gets to maintain the same force sensitivity that one had originally with the system in contact with the thermal equilibrium temperature T and its original quality factor. So this ratio is largely unchanged, apart from some other effects which I've discussed later in the series. Yeah.
There's something, so measurements like this, so the bandwidth you list there, I'm guessing is a bandwidth on some bandwidth analyzer, spectrum analyzer, or something like that?
Or it could be determined by, say, if you take a time series of the position of an oscillator, right? So it could be determined by your averaging time.
Sure. Okay. And so this right here, I guess what I'm wondering is how does the mechanical bandwidth tie into all this? Because it seems like cooling, broadening it would increase mechanical bandwidth. I'm not sure if that's sort of a relevant thing that you.
Yeah. So I think what we mean by measurement bandwidth is different than what we're thinking about in terms of the bandwidth.
So yeah, I'm just wondering if the mechanical bandwidth is important.
Well, I mean, so here you're essentially broadening so when you apply this cooling, you're broadening the line, right? So you're decreasing the Q, if you like, of the resonance, and making it apply it. While at the same time, you're decreasing the area under the curve. If you were to integrate the square as a function of frequency, right? You decrease the area under the curve. And the ratio that you're reducing the temperature by and the ratio that you reduce the Q by are approximately the same. But I think those results are not dependent on this parameter, right? Which is just right. Okay. So I don't know if I answered your question.
Why? I was trying to why you would want to do.
We will get to that. Yeah. So that's a very, very good question, and it turns out to be crucial for the measurements that we're going to talk about. Yeah. So we'll come back to that. Hang on a second. Okay, so let's put in some numbers before we discuss the cooling. So, since the sensitivity is going to wind up being similar anyway. So here's some devices. These are single crystal silicon cantilever beams. So they have a width of about 50 microns, length of 250 microns, thickness of around a third of a micron. And if I plug in some numbers for their geometry and materials properties and so forth, and measure Q factors. So if I have a cryogenic system, okay, with Q around 10 to the 5, we're in the regime already of enemies and force sensing. So this is about 10 enemies per reverse at 4 degree skeleton. And you can look at this formula, and now I've expanded it out in terms of how it depends, how K and how omega depend on the geometry of the device in question. So you can look at this formula and see that if you want to really make this minimum sensitivity smaller, you can make the cantilever small, you can lower the temperature, or you can raise the quality factor. so most of the measurements that I'm going to, or I guess all the measurements we discussed, as I mentioned before, the main limitation is thermal noise under ultimate force sensitivity. So also I just want to mention how one actually measures the displacement typically in these cantilever devices. So one way to do it, assuming your device is large enough, is to do it optically. So you can construct a fiber interferometer where one looks at light that interferes, where so the light comes out of the fiber, bounces off the end of the tip, and then comes back in the fiber. And that light can interfere with light that comes down and just simply reflects off the edge of the fiber. And so in doing that, I can generate fringes. It's essentially a low finesse cavity here. Okay, so one gets a signal from this interferometer that has a scale to it that's giving the wavelength. And so using kind of microwatt levels of power, which are typical, you can get kind of picometer per hertz sensitivity. And so it turns out that's more than sufficient to typically resolve the thermal peak that occurs in these oscillators. So this is a spectrum from one of the oscillators, kind of like the one on the previous slide, with similar dimensions, where this particular oscillator has a fairly low frequency because it's loaded with a heavy object, so it's frequency around 300 hertz. And the motion here is typically on the order of angstroms. And so having picometer per hertz is certainly sufficient for, so yeah.
What's the frequency of the cantilever without anything on it?
In this particular case, it was around 8 kilohertz, I believe. But so the point is that in general, you're not really limited by your ability to measure the displacement of the object. You're limited by the force sensitivity in these systems. And depending on what you're looking at, you can use other methods to measure displacement, capacitance. You could use a quadrant flow detector. You can get reasonable sensitivity with that. It's comparable to an interferometer, high finesse. You can also use a high finesse optical cavity to get much higher, much better displacement sensitivity. Okay, so now I just want to say a little about some examples of what kinds of measurements we can do with these detectors. So first thing I'd like to talk about is an experiment that was used to measure gravity at a short distance. So here, the idea is you've got a cantilever beam, put a test mass on the end of it. This is a gold cube. It's about 50 microns across, 50 microns wide, and 25 microns thick. It's sitting on a cantilever here that has a width of 50 microns and a length of 250 microns. And so by putting this dense piece of material on here, which weighs about a microgram, you've reduced the resonance frequency of this oscillator down from several kilohertz down to below kilohertz. And we have one of these fiber interferometers to measure the motion of this cantilever beam. And now underneath this device, one can place a mass and then look at the gravitational interaction between the mass underneath the device and the mass on the cantilever. So the mass here is a little bit complicated, and it's set that way in particular to get around some systematic effects and issues of the experiment. And so here, the mass that we're using in this experiment is arranged in this meandering wire type pattern. So the idea is that the material here is gold. So there's 100 micron wide sections of gold separated by 100 micron wide sections of silver that are microfabricated. And these have a depth of 100 microns into the device here. And the separation here between these two objects is on the order of around 20 microns. So the idea is that when this dense gold material is underneath the cantilever, the gravitational interaction between the two is enhanced relative to when the less dense silicon material is underneath the cantilever. And so if this device oscillates back and forth in this direction, there's going to be a force on this cantilever beam that's just due to the density modulation of this material. And so the idea here of breaking this up into several sections allows me to have, so this driving that device is attached onto a piezo actuator which provides this motion. And by separating this device into sections, it allows me to decouple the frequency that I'm driving this oscillator from the frequency that that the density modulation is driving the device. So in particular, this motion is occurring at some subharmonic of the frequency, and that allows me to avoid directly shaping this cantilever device simply because I'm shaping another mechanical object that's nearby.
I'm sorry, could you repeat that?
Yeah. So okay. So this mass here is divided into sections, right? So with varying densities. As the different densities move underneath this cantilever beam, the force on it is modulated, right? So the idea is this device is sitting on an actuator, and I'm going to actuate this device back and forth at some frequency. But the frequency that the thing moves is not the same frequency that the density modulation occurs at, because that's a higher frequency, because for one cycle of this, several of
Well, it
these...
goes across like 3.
Exactly, it goes across a few of these devices. Yeah, so I'm going to 3. So in this case, yeah, so we're driving this device at a third of the resonant frequency of this cantilever, where this density modulation is occurring at the resonance. So in addition, there's a membrane, silicon nitride membrane between the two, and the purpose of that is to eliminate other systematic effects. So for example, the Casimir force provides a very strong interaction between this cantilever and this driving mass, and by having a stiff silicon nitride shield membrane here that's coated with a conductor, we basically can provide an potential surface there that can essentially screen out the Casimir force, so that there's still a DC component of the Casimir force between the cantilever and the membrane, but it doesn't vary at the frequency that the density is modulated. So we basically reduce the Casimir force to some DC background, whereas the signal that's driving my cantilever at its resonance is due to this density modulation. So this device goes inside of a cryostat that's at liquid helium temperatures of 4 degrees Kelvin, and so we drive our piezoelectric actuator that's moving this driving mass, and we look at the voltage on the interferometer signal measuring the cantilever's displacement, and so we average over many periods of the oscillators, of the actuators, oscillation in a phase-dependent way. So after one period of the actuator, we may see garbage on the interferometer, but if I average over many periods, I'll start to see a signal, in fact, at the resonance frequency of the cantilever. And so I can take many of these sets of data averaged for very long times, and construct a plot of the force as a function of averaging time. And so if I do measurement of the device far away with the actuator not moving, I expect to see the force decrease like the square root of the averaging time, which in fact one sees here as a result of the thermal noise. Whereas if I have a force that's acting on the cantilever, it's a coherent force above thermal noise, I'll see some deviation from this expected behavior. Okay, so in this experiment, so the force for this particular, so sensitivity for this particular device, so we had a spring constant that was quite floppy as far as cantilevers go, so only 0.6 10 to the minus 3 newtons per meter, Q factor of around 80,000, frequency of about 300 hertz, and a temperature of about 10 Kelvin, so this gives us a minimum potential force of about 1 atom. And so this allows us to test these theories for deviations from Newtonian gravity at the level of about 100 times the Newtonian potential at a separation of around 25 electrons. And I'll show on a plot in a second which sort of theories we're able to test. But so one other important part of the experiment is that we implement feedback cooling. So this is not in many ways similar to the optical cooling that we've been talking about, but in this case it's implemented with a piezo device, which basically just provides a force on the cantilever. So the idea is that you measure the displacement of the cantilever, you take that signal and phase shift it, and then apply some gain, through some gain, a signal to a piezo stack such that you're phase shifting the signal by 90 degrees. So you measure the position of the feedback with a signal proportional to the velocity. So if you do this, you damp the motion of the object, And so this, what we essentially do here is we reduce the temperature and the quality factor by the same factor. In this case, for our experiment, we reduce it by a quality factor of 10. And at the end, still preserve the same sensitivity to forces. So the advantage of doing this is that it makes our experiment easier. So if I have this oscillator with a very, very high Q factor, if I have some kind of perturbation to the system, say there's an earthquake or somebody drops something on the roof of your building or something like that, then there's going to be a long time before that perturbation dies off, right? So the time it takes for the oscillator to bring down is very, very long. Whereas if I can do the measurement with a lower Q factor to keep the same sensitivity, then I can simply recover from these kind of fluctuations or perturbations much more easily. So that was our motivation, at least in this experiment, to do that. For the levitated sphere experiment I'm going to talk about later, there's more important motivation for us to really implement this, or some sort of cooling. But so here we cool by about a factor of 10 to make our life a little bit easier, at the expense of a little bit worse signal to noise, right? So now the main peak here is cut by a factor of 10. So depending on what your shock noise limited measurement is on position, you only want to extend that so far.
I have a question about the previous slide.
Yeah.
So you said you can measure force sensitivity at something around 100 times the Newtonian gravity limit.
Yeah.
Okay, so does that mean that means, I take that to mean that you can't resolve Newtonian gravity on its own?
That's right, that's right. So
But what did you see in the previous graph when you saw a modulation? What was that?
So that was, right, so that was, let me see, so in this case, here we generated an artificial signal.
Oh, okay.
Using the PZT that we used to feedback cool.
Oh, okay.
So yeah, so getting back to that question, so here, this is a graph